In this lecture, we're going to talk about stress-strain diagrams. Before we get into stress-strain diagrams, though, let's kind of back it up one level, and we'll talk about what we measure in a lab when we go to test a material. So we take a piece of steel or aluminum, some metal, or whatever we want to test. We go into the lab, we put it in the testing machine. It grips both ends of the material, and the cross head of the testing machine starts moving upward, applying a force to this bar. So here's my sketch of what that would look like over here on the right. Here's my specimen, and I'm not showing where it's gripped, but it's gripped in here. It's applying a force. And we can put a device called an extensometer on our material that actually measures the change in length of this material as it's being stretched out. From that data, we would have the force and the change in length at several different values of force as the test progresses. Now initially, the load change in length response for most metals anyway is linear. So it starts at zero force and you have zero extension. And as the force increases, the extension of the bar increases in a proportional way. So there's a straight line relationship. After a while though, you may apply some force and you get a disproportionate amount of change in length. And this curve starts to come over and maybe it takes this shape. And then at some level, the thing finally breaks over here. All right, so this is the force deflection diagram. One thing to note about this force deflection diagram is that if you were to say change the dimensions of the structure, even by keeping the material the same. So if you have a 1-inch diameter bar, and did a load deformation test, and took the same material and had a 2-inch diameter bar, you would get a different load deformation response for the same force level and the same gauge length. Initially, you would get less change in length for the larger cross-section material. Let's make a little note of that. All right, so just to say this again, we can go into the lab, we can measure the change in length of the material, that delta L for different levels of force. And even if we have the same material, different size specimens can give different force deflection plots. Somehow we need to take the effect of size out of this. What we want is we want a plot that can be good for any size specimen that we take for any particular material. This is important. If we have a large structure like a bridge, we're not going to be able to test an entire bridge girder in the lab, in most labs. But what we can do is we can take a small specimen out of that material that makes the bridge girder, take it down into the lab, find the stress strain behavior of that, and then apply it to anything of different sizes. So to take the effect of size out of the load deformation behavior, we plot a stress strain curve. Okay, let me make a new page. All right, so now instead of having a force versus deflection curve, we can take that force divided by a cross-sectional area and come up with a stress, and we can take our change in length divided by some initial length and come up with a strain. There's a little issue we have to talk about first, though, and that is the difference between what's called engineering stress and true stress. And to kind of illustrate this, if you have kind of a wide rubber band, it's probably easiest to see this. But the same thing happens with metal bars too. I'm going to draw my tension specimen horizontally. If I take and put in a load on a round bar, it's very imperceptible initially, with the human eye. But what happens is, as that bar stretches out in the axial direction, not only do we get strain or a change in length down the axis of the bar, but we also get a change in diameter of the bar. It's hard to draw very straight on this tablet. But what I'm trying to show in this picture is this final dimension, or instantaneous dimension, is going to be different than this initial dimension for the diameter. And so what that means is, as compared to our initial cross-sectional area, the instantaneous cross-sectional area is going to be different. It's going to be reduced. Now, when loads are low, there isn't much difference between the initial area and whatever this area is. But when the loads get higher and you start to have higher strains, there tends to be a much larger difference. So if we were to take the force that we measured from our first test and divide it by the original cross-sectional area and plot it versus what we're calling our engineering strain, which is our change in length divided by our original length, we get what's called an engineering stress-strain curve. All right, so our engineering stress is going to be defined as the force divided by the original cross-sectional area, and our strain, our engineering strain, we're going to define as the change in length of some initial gauge length over that initial gauge length. Okay. In contrast, we can define terms that are called the true stress and the true strain. You use a different color. The true stress is defined as the force divided by the instantaneous cross-sectional area. And the true strain is the instantaneous change in length divided by the instantaneous length. And at low levels of load, there's not much difference between the engineering and the true stress and strain behavior. Okay, so in the red curve, we kind of follow along this line. There's a certain level where there starts to be some deviation. Kind of running out of page here. And the true stress strain curve for a lot of engineering materials never really hits a peak and comes down. It just kind of keeps going up. Now in our class, we're mainly interested in the engineering stress and strain behavior. It's a lot easier to measure this. You have to have some instruments. They make them. You can measure the instantaneous cross-sectional area or the diameter of a round bar as you test it. And you can calculate the true strain from engineering strain. But it's a little bit less convenient than just the plain old engineering stress and strain. Force divided by the original cross-sectional area and the change in length divided by the initial length. And if you're down in this portion of the stress-strain curve, and this difference here is probably even a bit exaggerated, if you're down in this portion of the stress-strain curve where there is no difference, then essentially the engineering strain and the true strain, engineering stress and the true stress are the same quantities. In our class, we're going to deal with the engineering stress and strain. There are certain applications that you may be wanting to use the true stress and strain. If you want a lot of deformation in a structure, for example, if you were doing metal forming, such as stamping out of an automotive body panel, you want to use the true stress and strain quantities because you want to have a lot of deformation. So you'll be up in this upper region in this diagram. You want to account for those changes in dimensions that aren't really accounted for in the engineering stress and strain. If you're down in the elastic region, we'll talk about that soon. If you're down in this region of the curve where there's not a lot of change in dimensions, it really doesn't matter between this engineering and true stress definitions. But I just want you to be aware that there are different definitions of stress that are out there, as well as strain, and you may run across these different definitions. You should always understand what people are talking about when they talk about the stress-strain curve. All right, so in our class, we're going to use our engineering stress and strain. Let me make a new page. Let's go over some important parts of the stress-strain diagram. Even though stress-strain diagrams for different materials are different, a lot of stress-strain diagrams have some similar features. And the sketches that I'm going to make are pretty rough sketches just to illustrate some of these points. All right, so here's a typical stress-strain sketch behavior here. We start off with zero load, and we have zero change in length. So we're down here at this corner point. We increase the load, the stress increases, and the strain increases. And the initial portion of this, for a lot of materials, a lot of metals in particular, is a straight line. Then it starts to get into kind of this curvy portion that hits a peak, comes down from the peak a little bit, and it breaks. Well, the most obvious point that you can look at may be this one right here. The peak stress is known as the ultimate stress. And it simply is the highest point on the engineering stress-strain curve. Well, the next point you might look at would be this one over here at the end. That's our fracture stress. That's where the thing broke. There's some use for the fracture stress. The engineering fracture stress is not always a terribly useful quantity, but it's something that you can compute, and I'll show you how to get the true fracture stress out of it. So this is the stress level at which the material breaks. Fancy word for breaks is ruptured. So that's the stress at which the material ruptured. Now, one last point that we want to look at that's maybe not completely obvious, but it's going to be important for us, is somewhere around here, there's kind of a transition between a straight line and the curvy line part of this curve. I'm going to say maybe it's about here. That's known as the proportional limit stress. And simply, that's the stress level at which the relationship between stress and strain is no longer proportional. There's no longer a straight line relationship between stress and strain beyond this point. It can be kind of difficult for some materials to find this exact point, but if you plot a few stress-strain curves, you can kind of imagine putting a ruler up against here on your plot, or using some sort of software like Excel to find the slope of a straight line initially, and you can get an idea of where that proportional limit stress is based on that behavior. Now, I mentioned the fracture stress. There's a quantity that we can calculate called the true fracture stress. The true fracture stress is the final force, or the breaking or rupture force, divided by the final area of the cross-section of the specimen. After the specimen breaks, you can take those two pieces and you can measure the final diameter so you can get this final area. Now the breaking force can be found if you know what the fracture stress is. The breaking force is the initial area times the engineering fracture stress. So the true fracture stress can be found by taking the original cross-sectional area divided by the final cross-sectional area multiplied by the engineering fracture stress. And the true fracture stress is a quantity that is sometimes used in fatigue calculations and other purposes. What we're going to do next is we're going to take a look in a little bit more detail at this initial portion of the stress-strain curve. As I mentioned, most of the things that we're going to do in this class, we're not yielding the material. We want to avoid this anywhere getting near the ultimate stress. For design purposes, a lot of times you're going to be down in this region of the stress-strain curve. So let's look at this in just a little bit more detail. All right, so I've replotted this. You can think of this like rescaling your axes on the stress-strain curve and making a plot. And here's my straight line. Maybe my proportional limit stress is about here. We've talked about that already. And now we need to talk about something else called the yield stress of the material. When we have a specimen of metal, maybe, for example, a piece of steel, we take it down into the lab. We put a little bit of force on it. It's kind of like a spring. If the force is small, this may stretch out. I'm exaggerating the stretching. But then when we let go of the load, it goes back to its original dimensions. This is known as elastic material behavior. It's kind of like a rubber band. Some people call a rubber band an elastic. So you take the rubber band and you stretch it out, you let go of it, and it snaps back to its original dimensions. So what's happening then is at low stress levels, you're going up this curve to some stress level corresponding to some strain, and then you let go of it, and it goes back to zero stress and zero strain. However, there's a certain level of stress by which you exceed this, you start to have permanent deformation. And that's how we're going to define the yield stress. Let me write this down. It's going to be a fairly important quantity for us in engineering design purposes. Stress level is which you start to get permanent deformation. You can do this for yourself if you want. If you have a paper clip laying around, you can take that paper clip and you can open it up just a little bit, just enough to slide in maybe a couple sheets of paper, and then let go of that paper clip. And that paper clip will go back to its original dimensions. But if you take that paper clip and bend it to maybe a 90-degree angle and then let go of it, it doesn't spring back all the way. It might spring back a little bit, but it's permanently deformed. So we have exceeded the yield stress of the material in that situation. The yield stress of the material is often around where this proportional limit stress is. Sometimes the yield stress and the proportional limit are pretty close to the same thing. Sometimes they're not. Different materials behave in different ways. A material like a low carbon steel, still kind of a sketch and not to scale, but it has what's known as an upper and lower yield point. So it has an upper yield point and a lower yield point. And at this point, it goes very straight line up into this upper yield stress. And then you start to have some permanent deformation. So let me just label this as low carbon steel. This would be something like what's called A36 structural steel. It's used in I-beams and civil engineering structural applications. But other materials are kind of like that sketch that I drew on the previous page, where we have our stress and strain curve, and it's just kind of curvy. Now here's the thing about doing a tension test and defining my yield stress as the place where we start to get permanent deformation. If you think about it, when you go into the lab and you want to do a tension test, you're not going to stop it and measure the specimen every single moment you apply another incremental load. What you do is you put it in the testing machine, you apply the load until it breaks. So that gets to be a little bit harder to answer this question. When do we start to get permanent deformation? Maybe in this diagram it's around this point, but unless we've actually measured the dimensions, we can't really say for sure. Well, there's a shortcut way to estimate what the yield stress is, and we'll talk about that. If it's not clearly defined like it is for the low carbon steel down here, we're going to use a method called the 0.2% offset method. And this method would be used for materials like aluminum alloys. Some higher strength steels have this kind of curvy behavior, and so forth. All right, so let's take a look at this 0.2% offset yield stress method to determine the yield strength. Here's my stress strain curve. My proportional limit is fairly well defined, and the linear portion is fairly well established too. There's a distinct region where stress and strain are related to each other through this proportional relationship. Now, the 0.2% offset yield stress method is pretty easy to apply. It can be kind of a mouthful to explain. But here's what we do. 0.2% is, because it's percentage or things times 100, is corresponding to 0.002, whatever our units are, inches per inch for strain. And so what you do is you find along the strain axis 0.002, and you draw a line, not straight up, but you draw a line at the same slope as this initial portion of your stress strain curve. So that's my dashed line, my dashed red line in this figure. The point of intersection of your stress strain curve and this dashed line is the 0.2% offset yield stress. All right, so let's write that down. Let's write those steps down. We find that 0.2% or 0.002 inches per inch on our x-axis. Second step, draw a line parallel to our initial stress strain curve. And then finally, the point of intersection is our 0.2% offset yield stress. So that's a way to estimate where we have permanent deformation. Now, some people, for other materials, some materials, they might use a 0.5% offset and so forth. Some materials, you don't even need to use an offset because it's pretty clear when they've yielded. Typically, you will have a homework problem that involves the 0.2% offset method, where you're given forces and deformations. You convert those into stress and strain, make a plot, and then you can put a ruler up to it, make a best fit line in the straight line portion, and then take that ruler and slide it over with that same slope to find your 0.2% offset yield stress. Now, while we're here, we should talk about a couple other terms associated with stress strain curves. And one of them is called the modulus of elasticity. This slope has that special name of the modulus of elasticity. In the straight line portion that we see for a lot of materials, metals in particular, there's a certain change in stress per change in strain. Okay, it's the slope of the straight line portion of our stress strain diagram. The symbol that we're going to use for the modulus of elasticity is E. So it's the rise over the run. But we need to note this is only for stress levels that are less than our proportional limit stress. So we have to be in that range below the proportional limit. The units of the modulus of elasticity are the same as the units of stress because strain is dimensionless. The number for the modulus of elasticity is usually much higher than any number that you would get for stress, however. Because the strains in most engineering materials are very small, stresses may be on the level of KSI or megapascals. Strains might be on the order of 10 to the minus 3 or 10 to the minus 6. So we end up with gigapascals, typically for a unit of modulus of elasticity, or millions of PSI, in MSI, or 10 to the 3 KSI for those units. Now, one thing to keep in mind if you work with stress strain curves is that the stress strain curve of a material can depend on its temperature. In general, most materials tend to behave in a more brittle fashion when they're at colder temperatures. And by a more brittle fashion, what I mean is it may have this linear region, but it doesn't have a lot of strain before it breaks. Whereas at higher temperatures, you may have the same modulus of elasticity, but it may yield sooner, and you may have a lot more strain before it finally does break. So this would be a material at low temperature, and this would be a material at higher temperatures. You may have seen an experiment where somebody takes a rose and dips it in liquid nitrogen, and then the rose shatters when they smash it up against the table. That's an example of the material behaving in a much more brittle fashion when it's at the low temperature as opposed to more flexible and compliant when it's at a higher temperature. Another good example of this, it's been speculated that the steel that was used in the Titanic had a ductile to brittle transition temperature that was fine in the warm water port where the ship was built, but dipped below that transition temperature in the icy water when it was near the icebergs. And so when it hit the iceberg, instead of it deforming as much, it simply cracked quickly, and those cracks ran very easily in that material. So that would be an example of steel behaving more brittle at a certain temperature as opposed to a higher temperature. All right, one last thing we want to talk about are a couple material properties. Now, if we wanted to find out what the strain was at any particular level of stress, we could look in a book, we can find the stress strain curve, and we can use the chart. We can say, okay, at this level of stress, we have this much strain. Or if we're in the elastic region, below the proportional limit stress, we can say that this much stress, we have this much strain. But if we're in the elastic region, below that proportional limit stress, we don't really need to use a chart because we know what the equation of the straight line is if we know the modulus of elasticity. The equation of a straight line is y is equal to mx plus b, but on a stress-strain diagram, instead of y, we have sigma. Instead of the slope m, we have the modulus of elasticity e for our slope. Instead of x, we have epsilon. If we have zero strain and zero stress, our intercept is equal to 0. So the equation of this line is known as Hooke's law. Another way that we can get to Hooke's law is if we think of a spring. We apply some force to a spring and the thing stretches out. We plot the force versus change in deflection behavior, and the slope of that line is our spring constant k, and we say that the spring equation is F is equal to k times delta x. The spring equation and the stress equation for Hooke's law are the same. It says that the stress is proportional to the strain and vice versa. Right. So instead of having tables of stress strain curves for different materials, if I know I'm below the proportional limit stress, all I need is a table that has the modulus of elasticity in it and an understanding of this formula. Then I can rearrange this. If I know stress and I want to find strain, I divide it by the modulus of elasticity. If I have strain and I want to find stress, then I multiply it by the modulus of elasticity. We'll do an example here in just a moment. It is important to make note, though, that this equation is only valid for situations when the stress level is less than your proportional limit stress. The modulus of elasticity is a material property, and so is our last thing that we're going to talk about, Poisson's ratio. It is also a material property. Poisson's ratio has to do with the fact that if we have a bar and we put it in tension, not only does the bar get longer, but the diameter decreases. We can define an axial strain in this bar, as we've done before, as the change in length divided by the initial length. And you can see that this gets longer, so that's a positive strain. But at the same time, we also have a strain that we can define in the diametral direction. And that would be the change in diameter divided by the initial diameter. Now, since this bar and most materials get skinnier when you extend them, pull on them in tension, this diametral strain tends to be a negative number. The quantity called Poisson's ratio is defined as the ratio of the diametral strain to the axial strain with a negative sign thrown in to make sure that we get a positive material property. So it's the ratio of the diametral to the axial strain. If you have a square cross-section bar, the same thing happens. It's a little bit harder for me to draw. Maybe I'll make it rectangular. But we have some initial dimensions. That's a width and a thickness. And if we put some loads on it, the bar stretches out, and you have some final width and some final thickness dimension. So you get strain in those directions as well. You can find the change in width divided by the initial width, or the change in thickness divided by the initial thickness. In that case, instead of calling it the diametral direction, what we would say is that's the transverse direction. So some people will write this as the negative of the transverse strain divided by the axial strain. And for most engineering materials, the value is somewhere, engineering metals anyway, the value is somewhere around 0.3. So for aluminum, Poisson's ratio may be around 0.25. For steel, maybe around 0.3, 0.33. Rubber and cork are some common extremes. Rubber has Poisson's ratio of around 0.5, and cork has Poisson's ratio of around 0. That's why when you pull a cork out of a wine bottle, it's hard to do. It kind of can get jammed in there. It doesn't want to get skinnier when you pull on it. That's a good thing for cork. Well, so now we have a couple new material properties that we just learned about. Let's get set up and do an example. Okay, so for this example, we're going to take a look at a steel bar. The modulus of elasticity of steel is around 30 times 10 to the 3 KSI. Poisson's ratio of 0.3. This material with a yield strength of 50 KSI, an initial length of 4 feet, an initial diameter of 1 inch. And what we want to do is we want to find the change in length and the change in diameter of this bar if we put a 10,000 pound or 10 kip load on it. All right, so one thing that we need to do is to figure out what the stress level is in this material when we put 10,000 pounds on it. 1 inch diameter bar, 1 inch is not a big length, but a material like steel is pretty strong. So let's see what's going on. So if we calculate the stress as the force divided by the original cross-sectional area, that would be 10,000 pounds divided by pi over 4 times 1 squared, inches squared. I end up calculating this to be 12.7 KSI. All right, so we have a stress of 12.7 KSI, and the yield strength, if we can assume that the yield strength and the proportional limit stress are pretty close to one another, we should be below the proportional limit strength for this material, so we can use Hooke's law to relate stress and strain. And I can write this down. This is a valid thing to write down now. Sigma is equal to E epsilon. I know that on the left-hand side, I have 12.7 times 10 to the 3 PSI. Over on the right-hand side, I have 30 times 10 to the 6 PSI. Notice I'm putting everything in my base unit. And then over here, the strain, I can say that strain is the change in length divided by my initial length. So if I want the change in length of this bar, I can find that by rearranging these. 12.7 times 10 to the 3 divided by 30 times 10 to the 6 times my initial length of 4 feet or 48 inches. If I do this calculation, I end up with a change in length of 20.4 times 10 to the minus 3 inches. Now for the next step, we're going to find the change in diameter of the bar at this level of load. The diametral strain is related to the change in diameter divided by the initial diameter. Since I have a 1 inch initial diameter bar, this would be the initial diameter times the diametral strain. I know that Poisson's ratio relates diametral strain to axial strain. And in this equation, I want to emphasize that this is axial stress and strain. So if I rearrange this, the diametral strain is equal to minus Poisson's ratio times the axial strain. So to put that into my delta D formula, I have minus Poisson's ratio times the axial strain times the initial dimension of the bar. For this particular problem, I have minus 0.3 for my Poisson's ratio. The axial strain is the change in length divided by the initial length. I have units of inches on the top and the bottom, and then times my 1 inch. If I put all these numbers together, I end up with a fairly small number. It's negative, indicating the diameter gets smaller. Negative 127.5 times 10 to the minus 6 inches. So let's think about this. We have a steel bar that's 1 inch diameter. We put 10,000 pounds. That's a fairly significant amount of force. 10,000 pounds on it. And it only stretches out by 20 thousandths, just over 20 thousandths of an inch. And the diameter changes very, very little, just over 0.1 thousandth of an inch. So this is kind of interesting. Something that we're going to get out of this class is a little bit of steel can go a long way. It's very, very stiff. All right, that's it for this lecture. Next time, we'll get into shearing stress and strain.